Inside this semiconductor factory, silicon sand becomes wafers, microchips, and AI processors.
The full process transforms raw silicon into the tiny circuits that power modern technology.
The semiconductor journey begins with silica-rich sand prepared for purification. Washing removes clay, dust, and loose impurities from the sand. Screening creates a more uniform silica feed for purification. Prepared silica enters high-temperature purification equipment. The first purification stage creates metallurgical-grade silicon.
After cooling, silicon becomes hard, metallic-looking chunks.
Silicon chunks are inspected before the next purification stage.
Further purification creates high-purity polysilicon for semiconductor wafers. High-purity polysilicon forms as clean, solid material for crystal growth.
Polysilicon is handled carefully to protect purity. High-purity polysilicon is loaded for crystal ingot growth.
The furnace creates the conditions needed to grow a single crystal.
A seed crystal slowly pulls a cylindrical silicon ingot from purified silicon. The grown silicon ingot is removed and prepared for shaping.
Ingot inspection checks the crystal before wafer production. Grinding shapes the ingot to a precise diameter for wafer slicing.
The ingot ends are trimmed before slicing into wafers.
A diamond wire saw slices the ingot into thin wafers.
The diamond wire saw cuts the ingot into thin silicon wafers.
Freshly sliced wafers are fragile and must be handled carefully. Lapping removes slicing marks and improves wafer flatness.
Edge rounding reduces the risk of wafer cracking during later processing.
Wafers are loaded for precision polishing.
Polishing creates the ultra-flat surface needed for semiconductor circuits.
Cleaning removes particles before wafers enter the fabrication cleanroom.
Clean wafers are dried and moved into sealed carriers.
Polished wafers are inspected before circuit fabrication begins.
Cleanroom workers wear full protective suits to prevent contamination. Air showers remove particles before workers enter the fabrication area. Sealed wafer carriers move through the cleanroom with minimal human contact. The wafers enter an oxidation furnace to form a thin insulating layer.
Oxidation forms a thin protective layer on the silicon surface.
After oxidation, wafers are inspected for surface uniformity.
The wafer is positioned for a thin layer of photoresist. Spin coating spreads photoresist into an even thin layer.
A soft bake stabilizes the photoresist before exposure. The coated wafer enters the photolithography scanner. Photolithography transfers tiny circuit patterns onto the photoresist. Development reveals the pattern that will guide the next processing step.
Inspection checks whether the tiny patterns are aligned correctly.
The patterned wafer enters a plasma etching chamber.
Etching removes selected material and transfers the pattern into the wafer layer.
After etching, remaining photoresist is removed.
Post-etch cleaning removes particles before the next processing step.
The wafer enters an ion implanter to adjust electrical properties.
Ion implantation changes selected regions so they conduct electricity in precise ways.
Annealing activates implanted regions and repairs crystal damage. Thin film deposition adds new material layers onto the wafer.
Deposition creates thin material layers, only a tiny fraction of a hair thick.
Metal deposition adds conductive layers used for chip connections.
Atomic layer deposition creates extremely controlled thin films. After deposition, polishing flattens the wafer surface. Chemical-mechanical polishing keeps layers flat for precise circuit building.
A chip is built through many repeated cycles of coating, exposure, etching, implantation, deposition, and polishing.
Metal interconnect layers create pathways that connect millions or billions of circuit elements.
Inspection finds defects before the wafer continues to the next process. Automated transport reduces contamination and human contact. Between critical steps, wafers are cleaned to remove microscopic contamination. A protective passivation layer helps shield the finished circuits. The completed wafer is visually inspected before electrical testing.
Wafer probing tests each chip die before the wafer is cut.
Electrical testing checks which dies meet performance requirements.
Test results guide which dies will become packaged chips.
Before dicing, the wafer is mounted on support tape.
The dicing saw aligns to the streets between chip dies. Precision dicing cuts the wafer into thousands of individual chip dies.
Dies are lifted from the diced wafer for packaging.
Dies are sorted before they move into packaging. Packaging begins with clean substrates that will hold each chip die. The die bonding machine aligns each tiny die onto a substrate. Die bonding attaches the silicon die to its package substrate. Wire bonding connects the die to the package substrate with extremely fine wires. Advanced packages may use flip chip bonding for dense, high-speed connections. Underfill reinforces the tiny connections inside advanced packages.
Molding protects delicate chip assemblies from damage.
Encapsulation creates a protective chip package. The package panel is separated into individual microchips. High-performance processors receive heat spreaders to help manage temperature.
Visual inspection checks every finished package before electrical testing.
Final testing checks whether each packaged chip works correctly.
Each chip is tested for function, speed, and reliability. High-performance processors are sorted after final testing. Finished chips are packed into clean anti-static trays.
Chip trays are packed into blank cartons for shipment.
Finished chips are stored in a clean, controlled warehouse. The finished chips are prepared for electronics manufacturing supply chains.
Microchips leave the factory to power computers, vehicles, robots, and data centers.
The first stage turns silica sand into high-purity polysilicon.
Crystal growth turns polysilicon into a long cylindrical silicon ingot. The ingot becomes thin polished wafers ready for cleanroom fabrication. Cleanroom control protects wafers from microscopic contamination. Lithography creates microscopic patterns that define the chip circuits. Etching and implantation shape the wafer and adjust its electrical behavior.
Deposition and polishing build flat layers for increasingly complex circuits. Metal interconnect layers connect the tiny circuit elements into a working chip design.
Wafer testing and dicing turn a processed wafer into individual chip dies. Packaging protects the silicon die and connects it to the outside world. Final testing and packing prepare chips for the global electronics supply chain.
Silica sand is the starting point for the semiconductor process.
Purified silicon has a hard metallic appearance before it becomes a crystal ingot.
The silicon ingot must be uniform before it is sliced into wafers.
A polished wafer provides the flat surface needed for microscopic circuits. After many process cycles, the wafer contains thousands of repeated chip patterns. Each tiny die is one future microchip before packaging. Packaging turns fragile silicon dies into usable microchips. Semiconductor fabrication depends on precision tools working inside an ultra-clean environment. Even microscopic particles can damage circuits, so cleanroom control is essential. Automation helps move wafers precisely while reducing contamination risk. Each wafer changes gradually as layers are added, patterned, etched, and polished. Back-end manufacturing turns wafer dies into finished chip packages.
From one wafer,
the factory creates many chip packages for modern electronics. AI processors are shipped to power servers, data centers, and advanced computing systems.
Semiconductor manufacturing begins by increasing silicon purity step by step.
The ingot is sliced and polished into the thin wafers that carry the circuits.
Lithography defines the tiny shapes that guide the entire chip-making process.
Etching shapes the layers, while implantation adjusts electrical behavior. Deposition adds layers, and polishing keeps each layer flat enough for the next one. Interconnect layers link the tiny devices into working chip circuits.
Before cutting, the factory tests which chip dies work correctly.
Dicing separates the processed wafer into individual chip dies. Packaging protects the die and connects it to the outside world. Final testing confirms which chips are ready for shipment. What begins as silicon becomes the foundation of artificial intelligence and modern electronics. This factory is one of the most precise manufacturing environments in the world. Back-end manufacturing turns fragile silicon dies into reliable chip packages. Finished chips are stored carefully before moving into the global technology supply chain. Microchips leave the factory to become part of future devices and AI systems.
The key steps are purification, crystal growth, wafer preparation, cleanroom fabrication, testing, dicing. These chips can power phones, vehicles, robots, data centers, and AI systems.
First, silica sand becomes high-purity polysilicon.
Next, polysilicon becomes ingots, and ingots become polished wafers. Then, cleanroom tools pattern and etch microscopic circuit layers.
Layer by layer, the wafer becomes a complete circuit system. After testing, the wafer is cut into individual chip dies.
Finally, dies become tested microchips and AI processors, ready for technology products. From silicon sand to AI processors, every stage depends on purity, precision, cleanroom control, testing, and advanced packaging. Thank you for watching Mega Processing Tech. Subscribe, like, share, and comment what high-tech factory we should explore next.